Hi, I am Darren Hong, and my teammates are Matthias Huijie, Sutu Sheyao, Ms. Sharifah Nazia Sheikh Khaled, and Dr. Nazia Amran. So today we would like to present a proposed method that may lead to cure for Alzheimer's disease, which called rewriting the brain nanocarrier-assisted neurogenic reprogramming in Alzheimer's disease therapy. And first of all, Alzheimer's is currently the most common neurodegenerative disease and the leading cause of dementia among the elderly. Unfortunately, there is still no cure, and current treatment can only manage symptoms and slow down the progression. That's why we are motivated to find a feasible and effective solution. And not only that, Alzheimer's is a progressive disorder caused by the build-up amyloid beta plaques, tau changes, synaptic loss, and neuron degeneration. These changes lead to dementia, loss of cognitive abilities, behavioral issues, and eventually death. So in worldwide, there are over 57 million people living with dementia, which is around 60% of them are from low and middle income countries. Alzheimer's is also the 7th leading cause of death globally, with nearly 10 million cases diagnosed each year. But in 2019, dementia care cost an estimated $1.3 trillion, nearly half of which was due to unpaid caregiving by family members. Thus, this rising global burden shows how urgent it is to find effective treatment that can not only slow down the disease, but actually reverse it. So in the past, treatment mainly focused on targeting amyloid beta plaque using the immunotherapies and enzyme inhibitors. However, most of these fail to show real improvement in patients. A few drugs like lecanemab and donanemab have shown minor effect, but nothing truly groundbreaking. Because of this, research focus is now shifting to another protein called tau. Tau plays a key role in maintaining the shape and stability of nerve cells. It also helps with cargo transport inside neurons. When tau becomes abnormal, it forms tangles, leading to cell damage and death. So, targeting tau offers a promising new direction for treatment. At the same time, there is growing interest in the role of microRNA in Alzheimer's disease. These are small RNA molecules that can regulate gene expression, and one of them, called MIR124, is specific to the brain and is involved in neuron development and survival. And research shows that the MIR124 levels are lower in Alzheimer's patients, suggesting it may be a valuable therapeutic target. In summary, our approach looks at combining the targeting of tau protein with the delivery of MIR124 to protect brain cells and possibly regenerate them. We believe this strategy holds real promise in advancing Alzheimer's disease treatment. And furthermore, our objective for this research is to propose a novel therapeutic approach, which is the development of a tau-targeted nanocarrier system for the delivery of MIR124 aimed at promoting localized neurogeneration in Alzheimer's disease. So, first of all, we begin with nanoparticle synthesis and surface functionalization. The goal here is to create tiny particles that can carry our therapeutic molecule, microRNA-124, into the body. We also add special molecules on the surface so that the nanoparticles can cross the blood-brain barrier and accurately target the abnormal tau protein involved in Alzheimer's disease. So second, we move on to the nanoparticle characterization. At this stage, we examine the properties of the nanoparticles to ensure that they are in the right size, stable, and safe. This helps us confirm that they can circulate properly in the body and reach the brain without breaking apart or causing unwanted reaction. And the third step is in vitro cellular uptake and targeting. Here we test the nanoparticles on brain cells in the lab, and we want to see if they can successfully enter the cell and attach to their intended target. So this step gives us the early evidence that the treatment is likely to work as planned. Following that, we have a neurogenic reprogramming and neuroprotection assay. In this stage, is focused on the therapeutic effect. We check if the nanoparticle can protect nerve cells from Alzheimer's damage and encourage the growth of new, healthy neurons. This is crucial to show how that our treatment does more than just reach the brain, but also it actively helps to repair it. And finally, we reach in vivo biodistribution and therapeutic evaluation. In this final stage, we test the treatment in a living mouse model of Alzheimer's disease, and we observe where the nanoparticle travel in the body, how much reach to the brain, and whether they lead to real improvement in memory, brain health, and overall symptoms. So in the end, together with these 5 steps, help us to design, test, and evaluate potential cure for Alzheimer's disease, one that target the root cause and support the true brain regeneration. In conclusion, our research presents a novel multifunctional nanotherapy for Alzheimer's disease, We developed a poly nanoparticle that is co-functionalized with two key targeting agents, which are the angiopep2, which enables the nanoparticle to cross the blood-brain barrier by binding to low-density lipoprotein receptor related to protein 1, and a tau-specific monoclonal antibody, which allows the nanoparticle to bind directly to intracellular tau protein, one of the core hallmarks of Alzheimer's pathology. And the nanoparticle is loaded with microRNA 124, a small regulatory RNA known for promoting neuronal differentiation and suppressing pathway that lead to glial cell inflammation. This means the nanoparticle does more than just protect neuron, but also has the potential to reprogram other brain cells into neuron, offering a regenerative effect, unlike the previous study, and focus on microRNA therapy or only on tau targeting antibodies. Our approach combines both into a single delivery platform. This improves targeting accuracy, reduce unintended effect, and enhance therapeutic potential. So we are also first to demonstrate this dual targeted system using poly as the nanoparticle base. We hypothesize that delivering microRNA in this way could promote the transformation of neuroblastoma cell and astrocyte into neuron. In the both cell-based and animal models, the treatment shows strong neuroprotective effect and signs of neurogenesis. So that's mean not only are brain cell protected, but new neuron-like cells are also forming. So to summarize all that, we have developed a first-of-its-kind therapeutic nanoparticle that cross the blood-brain barrier, target tau protein inside the brain cell, delivering microRNA R124, and promote the both protection and regeneration of proton neuron. This strategy represents a major step forward in the field of neurodegenerative disease therapy, especially for Alzheimer's disease. It lays the foundation for future treatment and that don't just slow down the disease, but potentially help reverse its damage. So that's all.